though. I appreciate it. Yes, thank you for offering. Yeah. Oh, yes.
We do well on Monday.
Yes, I'm very glad to hear that. Wait, what was your name again? I'm sorry. Jude.
Yeah.
Ah, like Jude, like in the song. Hey,
Yeah,
Jude.
like in Beatles.
Very
Exactly.
good. Ah, very nice. So, are you a Beatles fan then? Who isn't? Exactly. Very good. Oh, that's cute. Yeah. My mom's name is Judy.
Oh, wow.
Yeah. I appreciate it. Oh, you were supposed to do that as well? Ah, it's okay. I appreciate it. I appreciate it. Yeah. Good stuff. Ah, I'm very glad to hear. Oh, thank you. Yes. I do. This is my 8th one. I have one more, but that other one is not super appropriate. It makes a joke. It makes a joke about well, using a Greek letter and using. Anyways, so it's not good. So I'm not gonna wear that one. So I'm out now this week. So I don't know. Maybe I'll have to create more for next week. Yeah. Yes. You a Yankees fan? You a Yankees fan? Or it's just for the style? No, no, no. Go Jays, right? Go Jays, of course. Next year's our year. So Jude and friends, does one of you have a calculator I could borrow? Yes? Oh, thank you. Sorry, what was your name? Sorry? Janur? Yeah. Thank you, Janur. How do you spell that? J-U-N-N-U-R. Okay, Janur. Okay, thank you. All right. Hello, hello, and welcome. Good morning, everyone. How are we all doing? Awesome. I'm very glad to hear. Let's. It's so empty for the day before the, or I guess the class before the test. It's like a lot more empty than I would expect. At least the last one. But let's get some energy still. So yeah, how are we doing today? That's what I like to hear. Very good. So. Today we're going to be mostly focusing on reviewing content for the test. Here's the deal though. So I prepared kind of two things we could do. I prepared some questions that go over reviewing things that are related to the test but not the same difficulty. Or we could do the practice test. Now, here's what I suggest. I'd like to do my material because I'm going to post a video that goes through the practice test. Is everyone okay with that? Who is not okay with that and wants to do the practice test now? For real? Okay, I'm sorry, but you're still getting outvoted. I'm sorry. So, but it's okay, because I'll post the video on the classroom and then you can watch it. Is that okay? Alrighty. So, today we are, oh, have a good one. Okay.
Last question.
Oh, no, I'm sorry, I have to.
Where can I find the practice test?
So that'll be on Child's Math. I'm sorry, I have to continue with this. Thank you. Okay, so sorry about that. So let's get started. Today we're going to be focusing on integration techniques, including symmetry, even and odd functions. We're also going to be talking about more substitutions and some Riemann sums. Alrighty, let's get started. So we'll let f of x be equal to the sine of x. The question asks, where does g, which is the area function of f, attain a maximum on the interval 0 to 2 pi. Now remember that g attains a maximum when g prime is equal to 0 or undefined. So we have to search for the critical numbers. So in order to find the critical numbers, let's take the derivative. G prime of x, remember that's going to be equal to the derivative of the integral from 0 to x of f of t dt. All right, so remember, we've got a theorem. It's pretty fundamental. So we'll use the fundamental theorem of calculus 1. This is just f of x. So g prime is equal to f of x. So those critical numbers are going to occur when sine of x is equal to 0. So what are the solutions of sine x is equal to 0? Well, remember that sine of x has zeros on integer multiples of pi. So 0, pi, and 2 pi. And those are the only places that's going to happen on our interval of 0 to 2 pi. Now remember, when optimizing on a closed bounded interval by our extreme value theorem, we have to check not only the critical numbers, but also the boundary points. The good thing is, our boundary points 0 and 2 pi are already in our critical numbers. So we just check those. So how do we check all of these? We need to compute g. So first off, what is g of x? G of x is the integral of 0 to x of sine of x dx, which we know by our fundamental theorem of calculus 2 is going to be negative cosine of x evaluated at 0 and, sine of t dt, negative cosine of t evaluated at 0 and x. So this is going to give us negative cosine of x plus cosine of 0. So it's going to be negative, let's write it like this, 1 minus cos of x. So that is g. So remember, we have to check the value of g at our 3 critical numbers. So here, g of 0 is equal to 1 minus 1, which is 0. G at pi is equal to 1 minus cos of pi is negative 1, which is 2. And g at 2 pi is equal to 1 minus, same thing. G at 2 pi is equal to g at 0 by periodicity, which is 0. So here, this is the max. Okay. So let's talk about it. Bless you. So this gives us our standard optimization technique, which we've used in previous weeks. This question's a little bit phrased differently, though, because now we have our optimization function is an integral. So I want to take a second to look at the geometric properties. Before we do that, is everyone okay with what we did just now? Yes. Sorry? The blank? Yes, it should be posted. Let's take a look at the here. Have you had a chance to look at the teams? Oh, can I see? Has anyone else been able to find these? Yeah. So let's take a look.
Oh, is it?
Yes. So right here, and then here we go.
Oh my God, I swear 2 seconds ago it was not there.
No worries. No worries. Yes, Michelle. How did we find the critical numbers? Yes, remember the critical numbers happen when our objective function has derivative 0 or when our objective function has undefined derivative. So the derivative of our objective function, the derivative g prime, right? G prime is equal to f. So we're looking for zeros of f. Does that make sense? Yeah. So we're looking for zeros of sine of x. Now, actually, as I was speaking, one thing we would note is we did not check where the derivative is undefined. Are there any places where sine of x is undefined? No. Sine of x is continuous everywhere. Yes?
Would it be easier to do this graphically or
Yes! That is exactly what we're going to look at right now. Very good point. So, let's look at the geometric intuition here. So, if we're going to plot, here's 0, here is 2 pi. Sine of x looks like this. This is pi. So notice, each of the critical numbers happen here, here, and here. Each of the critical numbers of g, those are the zeros of f. Notice, as we go farther and farther, as we integrate from this left bound at 0, we're going to accumulate more and more area. So the question is, where is the maximum area? Notice if we accumulate past pi, our total area is going down because we're accumulating negative area. So of course the maximum of our area function is going to happen at pi because we want to accumulate only positive area. Does that make sense? Very good. Okay, let's keep going. We're going to do some fun exercises today. So I'd like you guys to take this one and think about this one for a little bit. So I'm going to ask which of the following is true. E to the x is bigger than 1 plus x, equal to 1 plus x, or less than equal to 1 plus x for every value of x. Or none of the above. So take maybe 30 seconds and discuss with a neighbor. Michelle? Of course.
Okay, I have a question about the fundamental.
Yes.
Like when you use fundamental theorem calculus, like the first part, where, okay, so it's giving you a function, and it's telling you that the area is represented by this. So, when you're solving for the g prime of x, you're essentially finding the area under the curve at from a fixed point to
Yes,
an x
exactly.
point. So would it technically be that it's f of x minus f of 0?
No, you're thinking fundamental theorem number 2.
Okay.
That would be if there's no derivative sign. But the derivative sign means that we can move this variable inside.
Okay. That makes sense.
Yeah. We're just applying the theorem. If you want more background on why the theorem works, we'll talk about it after, okay?
Okay, thank you.
Yeah, of course. Okay, so let's talk about it. Have we had enough time? Okay, so who thinks the answer is A? Okay, who thinks the answer is not A? Okay, I'm sorry, the answer is A. But now I'd like to talk about why. What were some techniques that made us think that the answer was going to be A? Yeah. So you plugged in 2 examples and then decided that it's going to work for every x. Okay, so that's not convincing me. Yes?
Because each x grows much faster than 1 plus x.
That's true, but maybe we need some way to show that. And even if we know it grows faster, how do we know it doesn't start below? So, yes?
I think if we start at x equals 0, the y-intercept of 1 plus x is at 1, right? And
Yes.
at that point, g for the x is, I would say 2 point something.
So we're still plugging in points, though.
We're not, because then the function is
But how do we know it doesn't stop working as x goes towards the negative side? Yes?
There's only one spot where they intersect. So if
Okay.
you look on one side, you look on the other side. If it's greater on both sides, and they never.
Ah, that's a convincing argument. That does work. I actually really appreciate that. But it's not what I'm looking for. Did anyone use the hint that I gave? Yeah. Yes, you. Okay, that's reasonable. I want to be a little bit more sophisticated than just drawing the graph. One more, yeah? No. Well, I don't know if maybe you could construct an argument. Okay, so the answer is A. Let's talk about why. This was the argument that I gave. The tangent line to the curve e to the x at the point 0, 1 is y is equal to 1 plus x. We could find that by using our tangent line formula. Okay? So that's number one. That's our tangent line. The second thing is, what is the second derivative of e to the x? What's the second derivative of e to the x? E to the x, which is always positive. If the second derivative is positive, what does that tell us? It starts with a C. If the second derivative is positive, it is concave up. What does a concave up function, like what does that mean geometrically? It accelerates upward. A concave up function always lies above the tangent line. So this function is concave up everywhere, so it always lies above the tangent line. So it holds for every single value x. Very good. So who is convinced now that it holds for every x? We gave an argument where it holds for every x. Yes?
I'm sorry, I'm convinced.
Oh, you're convinced. That's good. I'm very glad. So obviously you won't be asked to give like a proof like what we just did, but at least now we should be sure for ourselves, phew, okay, at least I know that it's going to be greater than 1 plus. Now I can sleep at night knowing that e to the x is bigger than 1 plus x. Bigger or equal to. Yeah, yes. Concave up functions always are bigger than the tangent line, or above the tangent line. So I'm saying the tangent line to e to the x is 1 plus x. You would have to do more work to show that that's the case. You would need to find the derivative, etc. But because finding tangent lines, we did that back in week 3, I'm just skipping over that. Yeah. Okay, let's keep moving. I really appreciate the discussion, but also let's try and get to more stuff from the test. So here's another integral for you. Take 30 seconds and discuss with a neighbor. Did you still want to discuss the previous one? So the tangent line, we got it by taking the derivative. So the derivative of e to the x at 0 is just e to the 0, which is 1. That's the slope. And we know the intercept is 1 because e to the 0 is 1. So that's why e to the x has tangent line 1 plus x. So Betty, what are we thinking? Can I see?
I just, you know what, I have, yeah.
Very good. Yeah. 很棒. Is that right?
Oh, yeah.
很棒. 非常好. Very good. Hello.
What tangent line are you talking about for this function?
Remember the tangent line, so this is e to the x. The tangent line at the point 0, 1. The way we found that is we
How
need.
do you know it's 0, 1? Oh, it's because it's like where it intersects with 1 plus x.
Yes, remember the tangent line has the same slope and the same intercept, right? So how did we find it? Derivative of e to the x at x is equal to 0 is 1. So that's where we got our slope of 1. And then e to the x at x is equal to 0 is 1, which gives us this.
Okay.
So that's how we found the tangent line. Okay. Just remember, think back to the week 3 content. We did a lot of tangent lines back then. Yeah, good. Of course. U is?
X squared, I imagine?
Let's see.
Or, wait, would you say U sub is better here or integration by parts?
Good question. So the question was, which is better, U sub or integration by parts? So I'm going to let you answer that, and we'll discuss in like 30 seconds. You have an answer? Oh, you don't know how?
I don't know what to use.
So if you were on a test and you didn't know how, what would you do?
I would guess.
You would guess? Okay,
Guess C.
so can you give me a guess then?
No, like I would guess C. Like
Okay,
A, B, C, D,
but
E,
there's no C here, so I want to guess from you.
Like, okay, I feel like you can do U sub and integration by parts, but like, do I have to use both of them?
Don't use either. Very good. Okay, so, all right, let's try this one. So, who did a U sub here, or who's trying a U sub right now? Kind of. Does anyone want to share what value of u they chose? Yeah, Betty.
0.
Oh, no. I know you know the answer. So what value of u did someone choose who used a u sub? So maybe u sub's not the correct approach. Let's try this. I'm going to write, so we're integrating a function f. Let's call this f. F of x is x to the 5, 3 minus x squared, cosine of x. So what happens if we plug in negative x into our function f? So this is going to give us negative x to the power of 5, 3 minus negative x squared, cosine of negative x. So we can pull this negative sign out. This is going to give us negative x to the 5 over, when you square a negative number, it's the same as squaring a positive number. So 3 minus x squared. When you take the cosine of a negative number, it's the same as taking a cosine of a positive number. So we just got, this is negative f of x. Okay, so we just did this random calculation. So what does this random calculation tell us? Yeah. It's an odd function, which means that it's symmetric rotationally about the origin, which means that if we're computing a definite integral over a symmetric region, all of those areas are going to cancel out. So what's the final answer? 0. Integral of an odd function over a symmetric region is 0. So, yes? For a what? Will you be asked this question for a non-symmetric region? I don't know if it would be this question. I don't want to say whether you'll be asked something or not because I'm not sure. I don't see any of the midterms beforehand, but yes.
If the band was -1 to 2, would this be possible?
Possibly, yes, because it's continuous on, no, because there's a discontinuity at root 3, so no. But if you were asked this maybe from -1 to like 1.1, then you would need other techniques to solve it. So I just want to say this one more time. So the question was, if we were asked this to integrate from like -1 to 2, would this be possible? So my answer was no, but the reason why is because at x is equal to root 3, which is less than 2, there's a discontinuity. There's a infinite discontinuity, a vertical asymptote. So no, we won't be asked from -1 to 2, but it might be tricky if we were asked from -1 to like 1.1 or something. Anyways, let's move on. We'll let f of x be equal to ax minus x cubed. Let's find for which value of a does f have 0 critical points, 1 critical point, and 1 inflection point. I'm just going to do this one. How's that sound? So for 0, well, in order to find the number of critical points, let's find them. So the critical points happen when f prime of x is equal to 0 or undefined. So f prime of x is a minus 3x squared. If we set this equal to 0, that means x is going to be plus minus root a over 3. Okay. If we want 0 critical points, we want this x to be undefined. We want this no such x to exist. So if a is less than 0, then there are no values of x. If we want exactly 1 critical point, then we want the plus minus roots of x to be the same. So the only time this plus minus is going to be the same is if the inside is 0. So we have 1 critical point if a is equal to 0. So this is our answer for a and b. And then for c, what we need is the second derivative. So f double prime of x is going to be equal to negative 6x. What happened to our a term? Is there an a term in f double prime? No. So the number of inflection points is independent of a. A does not contribute anything to the number of inflection points. I'm going to tell you an interesting fact. A cubic function always has an inflection point. And did you know, so you know how most of the time we've been talking about odd symmetry about the origin? Rotational symmetry about the origin, and that's what our negative f of x equals f of negative x? Did you know cubic functions always have rotational symmetry about the inflection point? So there's always an inflection point, and there's always rotational symmetry around the inflection point. Now, just because it always has that symmetry does not mean cubics satisfy f of negative x equals negative f of x, because that only tells us rotational symmetry about the origin. Anyways, that's an interesting fact. In addition to, I should say this is like more admin stuff. In addition to the video that I'm going to post for taking up the last year's test 2, I'm also currently working on like a set of practice problems for the final, which are going to be more difficult than the ones in your textbook and also the ones in your stuff. But they're going to be very targeted to try and teach specific concepts. So I'm going to post that just after test 2, and hopefully that's helpful. Each question is there for a reason, to teach you one specific concept. Yes? Sorry? Where do I find I'll post them in the Teams. Yeah, everything will go in the Teams. Alrighty. So let's keep going. Let's keep going. I'm going to skip these questions here. We'll let a and b be positive numbers with a less than b. We want to compute the integral from a to b of e to the negative x squared dx. Now, we're given 2 other integrals. The way we're going to do this is let's just plot out this region here. So let's say this is negative a, this is 0, this is a, and then this is b. So we want this integral. We want this orange region here, which is the integral from a to b. In order to find it, we're given this integral here from negative a to a, and we're given this integral from 0 up to b. So in order to compute this integral, what I'd really like to do is find the area. So we want to compute this value, right? The integral from a to b. What I'd really like to do is have the integral from 0 to b and subtract off the integral from 0 to a. That's what I'd really like to do. So how could I do that? How could I find the integral from 0 to a and subtract that off? So is everyone okay with what I've done so far? How could I find the integral from 0 up to a? Yeah. Yeah. Exactly. E to the x squared, or e to the negative x squared, is even because of that square. So since this is an even function, we're going to use the even symmetry around this point. So this function is even. So since it's even, I'm going to substitute this one being equal to d, by the way. So this is d minus, this is 1/2 of the area from negative a to a. Is everyone okay with that? So half of the region is going to give us half of the area because our function's even. I'll say that one more time. Our function's even. It's symmetric about the origin. So if we take half the region just on one side from a to 0, that's going to be the same thing as half the region, the integral from negative a to a. Is that okay? Yes, this is a non-elementary integral. Exactly. We can't actually compute the integral. That's why I gave you C and D. Sorry? You will learn. Is anyone taking Math 2 ZZ3 in winter of next year? So everyone calls that Calc 4. That's actually called Calc 3 because the third one you take is differential equations. I tell every year's engineering this because I want this naming convention to change. Because that's not actually Calc 4. There's no such thing as Calc 4. So that's Calc 3, and that's where you'll learn how to actually compute this integral. So this is d minus c over 2. All right. Is this okay with everyone? Yes. Oh, yes. Good. Alrighty, let's keep going. Let's keep going. So let's evaluate the integral of x times x minus 1 to the power of 4. Notice this is a polynomial function. It's in factored form, but it's a polynomial, which means that it has an easy integral to evaluate if we know how to expand it. The difficult thing is I don't want to expand this, right? Taking a power of 4, we're going to have to expand 3 binomial multiplications. That's too much. So what we're going to do instead is make a clever u substitution that moves the translated term over to the other one, to the linear power. You see we have an x minus 1 translated. Let's move that minus 1 over to a different, to the linear term. So if we set u equal to x minus 1, then taking the derivative we have du is dx, and also x is equal to u plus 1. So if we substitute all of this information back into our function, we're going to get u plus 1 times u to the 4 du. And now this is easy to integrate because we only have to expand one term. This is integral of u to the 5 plus u to the 4 plus dx. And we can solve this in one step using our power rule. So now we can substitute back our value for u. 1/6 u plus, or x minus 1 to the power of 6 plus 1/5 x minus 1 to the power of 6 to the power of 5 plus c. Is everyone happy with this example? And in particular, how we chose u was we wanted to move that higher power over to the linear power term. Very good, very good. That's what I like to hear. So let's, oh, question. So when we make a u substitution, we have to change every single variable. So you notice how in the top line we had only x's? After we made the substitution, every single x turned into a u. Oh, very good. Thank you, thank you. This is a u. Thank you. Good catch. Alrighty. So now I'm going to give a problem to you. So can you compute 1 over 1 plus sine of x dx, integral of that? Take 30 seconds, take 45 seconds. Discuss this with your neighbors. Question?
No.
Oh, go ahead.
Yeah. No, I'm on a call.
You're sorry?
I'm on a call.
Oh, you're on a call. Sorry. I thought you were talking to me. U over 1 plus sine of
You replace u with u equals 1.
u is equal to 1? U over u plus sine of x. So actually, I don't even know how that would work because then you would, if you introduce another variable, then you have to partial integrate with, or you have to integrate with respect to only one variable.
It would work eventually.
Well, why don't you try that out and you can show us if you get the answer. Okay, so who thinks they have an answer for this one? You have an answer? You have a question. What's your question? Sorry? I can't hear you. Oh, did you do it right or wrong? We'll take a look in a sec. Yes.
I mean, I hope it's right, but it kind of looks like derivative of, sorry, part 10. Derivative of part 10.
looks like arctan. If we had an arctan, we would need a square. So you're thinking this is the root of sine x squared. If we were to do some sort of substitution, if we swapped that out for arctan, then we would need a chain rule if we took the derivative. So we're missing a chain rule. We're off by a factor of a 2 root x squared.
So what I first did, what I want to time to do is I multiply by the conjugate with minus sine.
Yes, bingo. For this one, we multiply by the conjugate. Now, I wanted to be tricky with this one because I wanted to be tricky because last week we did a lot of remember we did 1 over 1 plus e to the x? I wanted you to think it was add sine x, subtract sine x, which actually doesn't work for this one. Let's multiply by the conjugate. In our denominator, we're going to get 1 minus sine of x in the numerator, first off. Our denominator, we get 1 minus sine squared of x. What's that? What's our denominator? Cosine squared. So this is now 1 minus sine of x over cosine squared of x. If we rewrite using our identities, this is just secant squared of x minus tan of x secant of x. So now can we compute this integral? So the integral of secant squared of x, what's that? Tangent of x. And what's the integral of tangent of x secant of x dx? Yeah, I heard it over there. That one is secant of x plus c. So is everyone happy with this one? No? Which part? Which part? The whole thing. Do we at least get how we got from step to step? Alrighty. Yes, Michelle. So the derivative of tan x is secant squared. So that's why we. And the derivative of secant x is tan x secant of x. Alrighty, let's keep going. Let's keep going. I have another one. If you weren't happy with that one, you're gonna love this one. Let's evaluate the integral of x squared over root of 1 minus x to the 6. Take 30 seconds and talk with a neighbor.
Maybe the conjugate.
I was just wondering how I can access the last week's thing because it's like.
Oh yeah, it was
on here, right?
Yes, it should.
So like, is it the notes?
Yeah, the notes should be the slides.
It says like. I don't
Okay,
have access.
this is super weird. It's been I've been getting spam emails with this.
Oh, okay, yeah. 'Cause
So
I wasn't able to come last week, so I wanted to.
So can you send me an email and then I'm gonna repost the notes. I don't know why it's doing that. Thank you. So what if you said u is equal to x? Then the same thing is same integral.
That's the derivative, right?
Sorry?
Should you do that? Am I on the right track here?
That looks a lot more complicated to me.
Okay.
I see a solution in the bottom one, or the original. I don't see a solution in yours. If anything, I would simplify it back to the first one. Yeah. Yes.
So 1/3 sine inverse x cubed plus c. Like you just put x cubed here.
Beauty. Nice. You got it. All right, we've got one correct. Yes. Look. Let's see. What's your substitution? Yes. Bingo. Sorry? You have a substitution? No? No, I do. All right, let's do it together. Let's do it together. So we want to evaluate this integral. So for this one, here's the thing we should notice. We have an x squared in the numerator. We want to make a substitution which cancels out that x squared. So in particular, if we make a substitution using maybe x cubed, The derivative of x cubed is a multiple of x squared, so we can cancel out the thing in the numerator. So here's what I'm going to suggest. Let's rewrite our x to the 6 as x cubed squared. Who likes that? So this is now the integral of x squared over 1 minus x cubed squared dx. Then we'll set u equal to x cubed. Du equals to 3x squared dx. So if we move the 3 to the other side, 1/3 du is equal to x squared dx. So notice here we have an x squared dx. So we'll substitute everything at the same time. We have the integral of 1/3 du times 1 over root of 1 minus u squared. So what's this integral? What's the integral of the fraction side, the 1 over root of 1 minus u squared? That's arc sine of u. So this is 1/3 arc sine of u plus c, and we can substitute our u back in, so we get 1/3 arc sine of x cubed plus c. Beautiful. So you guys at the front, did you like this one?
Yeah, it was a fun.
This one is a fun one? I'm glad. Alrighty. So, any questions about this one? Yes. Generally, when you are looking for, so if you're looking for a u sub, you should always be looking for a function whose derivative exists in the numerator. So notice we see an x squared in the numerator. That should instantly signal, how can I substitute x cubed? That's what you're thinking. All right, shall we move on? Okie dokie. So, just in the interest of time, this is going to be homework. This one's not too bad. You've got a tangent here, you've got an x here. Do this one. This one also is going to be homework, but it's more difficult. Now we have now we have more. But this one could be, well, you can figure this one out. All right, let's do this sum. We haven't done enough sums today. So let's evaluate the sum from n is equal to 1 up to k of n squared times, or of n times n squared plus 1. We don't have any rules for multiplication, so let's expand this one out here. So this is going to be the sum from n is equal to 1 up to k of n cubed plus n. From here, does anyone remember our formula? This is, yeah? Yes, I'm going to write it like this. Oh, sorry, not n. Not n. K squared times k plus 1 squared all over 4 plus, does anyone else, does someone want to take the linear version? Who has the linear formula memorized? Yeah. So n? Good. The reason why I changed these indices is because this formula should still work no matter what letters we use. I don't want us to get attached to certain letters. The concepts of a sum are more important than the memorizing the letters themselves. All right, so this is our final answer. Notice that because our indexing variable, our for loop, if you will, the n variable is being summed over, our final answer should not have any n's inside of it. Okay, let's do, oh, we have a lot more time actually than the last class. So let's do this question. Compute using a left Riemann sum the area of the function on the interval 0 to 4 using interval length delta x going to 0. I'm changing the question. Okay, everyone take a couple minutes to figure this one out. And we're just going to write our final answer as a limit. All right, let's do this one. So this one we're just setting up as a limit. So here, let's do this. The integral from 0 to 4 of f of x dx, this is the limit as the number of rectangles goes to infinity. So we'll let n be the number of rectangles. We're going to make a sum from I is equal to 1 up to n. Now, let's actually draw out what this is representing. So here is 0 and here's 4. We're integrating a function over this region, and we want to sum up all of these rectangles. In particular, we want its width and its height. So its height is f of x star, where x star is some sample point on the interval, and delta x is our area, or sorry, our width of our rectangle. So in particular, let's write out the width and the height. The width is going to be the length of each interval. So in particular, it's going to be 4 minus 0, which is the length of the entire region, divided by the number of rectangles. So 4 minus 0 over n. And then our f value, we're going to have f of our sample point, x star, is going to be our left endpoint, 0, plus the length of the number of rectangles we've gone so far. So we're going to count the number of rectangles that we've gone so far and add up all their widths. So this is going to be 4 minus 0 over n times I. So if we were to rewrite this sum, this is the limit as n goes to infinity of the sum from I is equal to 1 up to n of 4 over n times 4n times I squared plus 1. Notice that if we were to evaluate this sum, so here actually I'm going to leave this as homework. I don't think we have time. If you evaluate this sum using the limit, notice we have a sum of I squareds. Those sum of I squareds is going to be an n cubed formula. That n cubed is going to cancel with our n cubed. It's going to give us some limit that we can evaluate using a rational function by analyzing the leading coefficients. Yes?
When it asks for left endpoints, does it matter? Because isn't the definite integral the same for the left endpoints, right endpoints?
Yes. So, yes. Don't worry about the left one for these infinite questions. I changed the question today because I wanted to. But yeah, the limit of all of the Riemann sums approaches the same value. Yes? It wouldn't matter because we're taking the limit to infinity. Usually they'll use this convention where you go n to 1, or 1 to n. All right, so, but let's say I wasn't convinced. So I want to do the exact same question again using our fundamental theorem of calculus. So in order to integrate this one, we'll integrate from 0 up to 4 of x squared plus 1 dx. This is going to be 1/3 x cubed plus x. So this is by our fundamental theorem of calculus 2. Integrated from x is equal to 0 up to 4. So this is going to give us 1/3 4 cubed minus, or plus 4 minus 0 cubed minus 0. So this is going to give us 64 over 3 plus 4, which is approximately, well, 63 over 3 is 21.33 plus 4. So it's approximately 25.33 repeated. All right, everyone happy with this definite integral? So let's say I still wasn't convinced, and I said, let's say I didn't even know how to integrate a question at all. The question says, compute using your McMaster calculator the area under the function x squared plus 1 on the interval 0 to 4. So thank you, Junder, for the calculator. So in order to do this one, what you're going to do is hit your integral button. Does everyone see the integral button right there? We're going to integrate x squared, comma, from 0 up to 4. Remember we said the answer is 25.33. Oh, no, sorry, 21.33. Maybe I made a mistake. Oh, I forgot x squared plus 1. Plus 1. There we go, 25.33. So if you're not sure how to integrate, you can at least use your calculator. Oh, how did I add in a number in the middle? Click Shift, and then do you see the delete button? Click Shift and then delete. That gives you insert mode. That? Yes. Actually, okay. Well, I have you all here. Did you know your function can add fraction, or your calculator can add fractions for you? Let's say I wanted this number as a fraction. I'm going to click Shift and then this ABC button here. It's 76 over 3. So everyone, make sure you're making use of all tools that you have available to you in the test. I'm going to post the makeup, or the last year's test take up today. Thank you so much, and I'll see you next week. Alrighty, and good luck on Monday. Hi there. Sorry?
Like 1.
Comma, 0, comma. There you go.
Thank you.
Oh, yes, please.
Like, how come it didn't matter if we used left endpoints, mid endpoints, and right endpoints, even though the question stated left?
So it doesn't matter because, so I changed my mind. N is approaching infinity. We should, so in class when you talked about the fundamental theorem of calculus, one of the big parts of the theorem is that it works as we approach, like as we approach infinity, every single integral value converge to each other. The limit of all of the integral values, regardless of endpoints, converge to the same number. That's the reason why we're allowed to apply this fundamental theorem.
If it like gave you an amount of some interval?
Yes, if they said use 4 intervals, then you can't. Oh, thank you very much. I appreciate it. See you next week. Have a good one. Take care. See you.
Well,
Yes,
I
sorry.
just wanted I want the explanation for this question again. I don't get it.
So the integral,
Yeah.
do you get this part here? If we have an even function, the integral from just half the region is equal to 1/2 of the whole region.
Yeah,
Yes.
I understand this is even.
Yes. Yes.
I just wrote that wrong. I put it here, but I know that this is even.
Sorry?
No, nothing. I'm talking.
Oh, sorry.
So like, where do you go from there? You know that's even.